Hello. In this video, we're going to continue with relatively short problem for Actuarial Exam 2 about Macaulay duration. We are going to consider some theoretical problems later. We're looking at 2017 SOA Sample Exam problem number 176. Given the Macaulay duration of a perpetuity-immediate, where the payments go on forever, find the duration of another perpetuity-immediate that's got double the interest rate, double the yield rate. I also, in addition to solving this problem, want to get across an important conceptual point at the beginning, and this will give us a chance to review formulas for present values of perpetuities. So we have an investor that buys a perpetuity immediate providing annual payments of 1. So perpetuity means it goes on forever. Immediate means the first payment is actually 1 year after time 0, with an annual effective interest rate of I and a Macaulay duration that's given to be 17.6 years. Our goal is to calculate the Macaulay duration in years when we double the interest rate, using an effective interest rate of 2i instead of I. So what's the conceptual point? The conceptual point pertains to whether or not we should expect the answer to be bigger or smaller than this original duration. So let's draw our timeline and think about this here. We have a perpetuity, payments going on forever, perpetuity immediate, meaning the first payment is at time 1, then 2, then 3, then 4, etc. These payments go on forever, and again, the duration is a weighted average of times of payment, okay? So in this case, that would be an infinite sum because it is a perpetuity. Think about that, what happens as I increases. As I increases, I goes up, that implies V goes down, and more than that, it implies that higher powers of V go down a lot faster, so to speak, okay, than when I is smaller. And because of that, that's going to mean these the present values of the payments that are far in the future are going to be not only a lot smaller, but actually even a lot smaller compared to the present value of the entire income stream. Okay, say that again. Not only for high times 10, 20, 30, etc., are the values of V of those powers going to be small, they're going to be a lot smaller. They're going to go down really fast as I increases. And those present values of those payments are going to be really small, microscopic, you might say. Even though the present value of the entire payment stream goes down, those go down a lot faster. And what that's going to mean is the Macaulay duration should be expected to be shorter as the interest rate goes up. So we should expect an answer less than 17.6. And when you look at the sample exam problem, the first 3 choices are less than 17.6, and the last 2 choices are bigger than 17.6. You should know that as I increases, the duration goes down. You should pick one of those first 3 answers, okay? It's got to be one of those 3. All right, but now let's go ahead and do the calculation. So what are we given? We're given that 17.6 is the duration at interest rate I. I could call that d of I if I like. And we have seen that that is a ratio where the bottom of the fraction is the present value of the entire payment stream. That would be A infinity in this case. And the top is not the present value of the entire payment stream as is, but instead really the present value of an increasing annuity, IA infinity in this case, because this is a perpetuity, these go on forever. If you want to write it out, you know, the top is really V plus 2V squared plus 3V cubed, etc. And the bottom is V plus V squared plus V cubed, etc. Okay? But you should know this, okay? That will be the Macaulay duration of a perpetuity immediate. And what is our goal? Our goal is to find what happens when we replace I by 2i. Find the duration at interest rate 2i, okay? So let's figure this out by reminding ourselves what the formulas are for these things. Now we know that I has formula 1 minus v to the n over I. And since v is between 0 and 1, that's going to mean v to the n goes to 0 as n goes to infinity. That means A infinity is 1 minus 0 over I, or just 1 over I. Okay, maybe you had that memorized. That's probably good if you did have that memorized, but that's a quick review of how to derive it. What about IA? Present value of an increasing annuity. With n payments, the formula is typically written as A double dot and I minus n v to the n over I. And excuse me, A double dot is going to have formula 1 plus I times an itself, which would be 1 plus I times 1 minus v to the n over I. And what happens to this expression as n goes to infinity? Well, certainly, once again, v to the n goes to 0. V is between 0 and 1. But what about n times v to the n? That still goes to 0 as well, even though n is increasing. You could try to maybe use the L'Hopital's rule or something like that from calculus to verify that. But this goes to 0 as well. So in the end, as n goes to infinity, we get IA sub infinity at interest rate I to be, this is 0, we get 1 plus I over I, 1 plus I over I, minus 0 all over I, which simplifies to 1 plus I over I squared. That you may be a little less likely to remember, though it probably is a good idea to remember anyway, but that is what the present value of an increasing annuity with an increasing perpetuity would be. Okay? So now we just need to use these things. Coming back up from this information here, 17.6 then is, we can put this thing in the top and this thing in the bottom. We can write this as 1 plus I over I squared, all over 1 over I. And then we can multiply the top and the bottom by I, and this simplifies to 1 plus I over I. And that's an equation we can solve for I. Once we've solved for I, then we can find d of 2i by using essentially the same formula with 2i in place of I. So let's solve for I here. Multiply both sides by I. We get 17.6 times I equals 1 plus I. Subtracting I from both sides gives 16.6 times I equals 1. So I is 1 over 16.6. 16.6, take its reciprocal. That's about 0.0602496. I'll store that in register 0. And we're almost done. Again, we want to find d of 2i. You can do the work. You're going to really get the same thing as you got here, except replace I with 2i. So this is going to be 1 plus 2i over 2i. Here's I again. Multiply it by 2. I'll store that in register 1. Add 1 to it. The numerator here is about 1.12048. Divide that by 2i, which is in register 1. And how about that? We get a nice answer. 9.3 years is the answer. And if you look at the options in that sample exam from 2017, this is option B. Okay, so again, here is the problem statement. But more importantly, realize that as the interest rate goes up for a given annuity like this, a perpetuity in this case, the Macaulay duration is going to go down.